Hi everyone, today's lesson is on circles. So let's get started. So the first thing that we are going to do is do a little bit of a warm-up and review what we know about circles already. So given this shape right here, this picture, we're going to say what's point O and all of the rest of these values. So let's see. So point O, which is right here, point O, that's our center of our circle. Okay, that's our center. OM, line segment OM, this is this length right here, OM, that's what we call a radius. A couple of things you need to remember, and that is a radius has a length. That's right there, that's a segment length. And when you see something that looks like this, OM, you can say, well, that's congruent to, let's say, OQ, okay? Because those are both radii and all radii are congruent. Or you could say something like this, OM without the line segment over it is going to give me a value. Like, let's say my length of my radius is 5. So be really careful with this and this. This is saying that this is a segment, and that segments are congruent to another segment. This is saying that it's a length, and lengths have a numeric value. Okay? All right, so moving on, we have line segment MN. So this length from here to here is what we call a chord. So CHORD. And then a chord is a segment that connects two sides, endpoints on the circle. We have line MN. So line MN, actually, see the arrows here? This goes through here. It's like a piercing. So this right here goes through it, and that's what we call a secant. Okay, secant pierces right through the circle, all right? A secant does contain the chord, all right? Or a secant can pierce right through the center also. Anyway, MQ, and where's MQ? MQ is this length right here, and that's what we call our diameter. And then we have line MQ. See the line like that? And that line is what we call a secant. We have line ML, which is up here. See this line? It touches my circle in one place, which we call right there that point of tangency. So ML is actually a tangent line. It's a tangent. And then point M is the point of tangency. Okay? So giving some definitions to this, this does go along with your note packet, but for a circle, you have a circle is the set of all points in a plane at a given distance from a given point. So there's our given point. And so a circle is the set of all points that are the same distance from one single point, okay? And this is a great segue to get to the next value or the next picture, because a radius is the length that goes from the center to a segment that joins the center to a point on the circle, okay? Now a chord is a little bit different. A chord connects two endpoints on the circle. So there's a chord, all right? You could have a chord this way, all right? You could have a chord this way. Now a diameter of a circle is actually something that's a line segment or a line that goes through, segment that goes through the center of the circle. So that's my diameter. And a diameter is made up of two radii. More than one radius is a radii. A secant, let me roll this up so you can see. A secant is one of those piercings. So this one, there's a center, goes through it intersects 2 points on the circle. And a line that's tangent, okay, touches my circle in 1 point. Okay, just 1 point. There it is, right there, that point of tangency. But you can have multiple tangent lines across your circle. See that? We have so many, infinite. A sphere, okay, so a sphere looks like this. Point here, we've got, let's try to make a sphere with dotted lines in the back, frown in back, happy in front. So a sphere is a set of all points in space that are a given distance from 1 point. So here's my point given. See, this is sort of like a radii, isn't it? Just like that, all the way around, okay? Concentric circles are circles that lie in the same plane and have the same center. So a concentric circle is sort of like a target, okay? It's a circle that has the same center as that. Now, circumscribed circle goes hand in hand with an inscribed shape. So basically, I could have a circle like this, and I could have a shape inside. Let's just say it's a four-sided figure. You would say the circle is circumscribed about the four-sided shape, or you could say the four-sided shape is inscribed within the circle. So you can say this two separate ways. So drawing a right triangle inscribed in a circle. So if you have a circle, okay, the only way to draw a right triangle in a circle is that it has to go through the center. And that's your diameter. So any of these right here would work. You could write it like that. You could write it like this, but it has to go through the center. The diameter is what we call your hypotenuse, okay? And then what you have is, what do you know about the midpoint of the hypotenuse? Well, the midpoint of the hypotenuse is the center of the circle. That's the center of the circle. All right. Where is the center of the circle? It's on my hypotenuse. If the legs of the right triangle are 6 and 8, okay, so I'm going to redraw this, but only have one right triangle so I can show you. So we have a circle. Okay, so we have our circle, and then we have our right triangle in here. All right, and it says that the legs of the right triangle are 6 and 8. Find the radius. So the legs are 6 and 8. So we'll say this is 6, and there's 8. That makes this 10. That's a 6, 8, 10. It's one of our special right triangles. That means that this radius right here is 5, and that radius here is 5. So what's the radius? The radius is 5. Now we're looking at this shape down here. Plane Z passes through the center of sphere 0, or actually this should be Q. So explain why QR is equal to QS and equal to QT. Well, they're all radii. And if this intersection of the plane and the sphere, if you look at this right here, this is a circle. Circle, by definition, where center Q is the middle of right here, has all radii are congruent. These are all the same values. If those are all the same values, then they're all equal distance, and it's a circle. So this one says, many circle terms also apply to spheres. So our center is X. Our radii, it looks like we have 3 radii. So we're going to, and usually you start with the center, and we could say XF is a radii, see from here to here. We have XF, we have XL from here to here, and then you have XI, okay, from here to here. So those are all radii. Chords, we have a chord that's GH, so GH. Diameter would be LI. And a secant, remember that's a piercing, so that does not pierce. This one, nope, here it is right here. So there's our piercing, so that's our secant. So we're going to say line, GH. We have a tangent. Now this is our tangent. Okay, now see how it touches in one place? That point right there, K, is the point of tangency. KJ is our tangent line. Line segment, line, this is a line segment. But you can also say it's a line. What you do need to remember is that it does need an arrow or a line segment on top. Notes, inscribed. Okay, so what you need to understand is when we did this was from our construction chapter where you have something inscribed inside. So here's our circle. The circle is circumscribed about the isosceles trapezoid. You can also say the isosceles trapezoid is inscribed in the circle. So you have 2 things you can say, because inscribed is drawn inside and circumscribed is drawn outside. So another thing I can say is that the circle is circumscribed about the triangle, or you can't say the triangle is inscribed within the circle. And thus you would say the square is circumscribed about the circle, or you can say the circle is inscribed within the circle is inscribed within the square. So you have different things that you can say. These are just one. There's two ways you can say each one of these. Inscribe each of the following polygons. So for this one right here, we want to inscribe an equilateral triangle. So equilateral triangle, that's going to work. We're going to have all three sides are congruent. We have a rectangle that's going to look something like this. The main part is what I hope you're noticing is that when you inscribe any shape, all the vertices have to touch the circle. So every one of my vertices have to touch the circle. If they don't, then it's not inscribed. So we have a pentagon. So let's see here. We have 1, 2, 3, 4, 5. Okay. But each corner has to touch. Right triangle, again, this goes through here. You've got this happening right here. Okay. Parallelogram. Now, you got to remember something. Parallelograms look like this. You have different kinds of parallelograms, of course, but parallelograms generally look like this. If I were to put my parallelogram, let me shrink it up a little bit, in here, okay, it's going to touch these two corners here, but not all four corners. So for a parallelogram, of course, if I had a square is going to touch all four corners, but a parallelogram is not. So therefore, just any parallelogram is not. So what's going to happen is if I were to say, can all parallelograms be inscribed in a circle? You would have to say no. So right here, we have no shape for a parallelogram, but all of these right here, inscribed each of the following polygons. That's done. These are called internally tangent circles. So meaning that if it's internally tangent, that the circle is inside another circle. So, and then they're internally tangent, meaning this line right here, that's going to touch both of those circles in just one place. Let me see if I get that better. There we go. So those are what we call internally tangent. So circles are internally tangent if one lies on the interior of the other, except for on the point of tangency. So these are all internally tangent. Of course, I could have also maybe even put another one in here. Okay. Externally tangent circles are externally tangent if each lies in the exterior of the other. So like here's my tangent line that I just missed that. So let me fix that. So here we go. They are externally tangent except for the point of tangent. Okay, meaning they're only going to be touching in one point, just like the point of at the point of tangency, and same with these. These are only going to touch in one point. Okay, these are internally tangent. These are externally tangent. And now these are what's called this green line right here. This line right here is what we call a common internally tangent line. Now I want you to look at this here. A common internally tangent line is a line that is tangent to both of these. Now it's not the same as this one here, which is an internally tangent circle. All right. It's a common internally tangent line. So what happens is this line right here touches both of the circles in one point. But the trick is for this one is that it has to intersect the segment that joins the center of the two circles. So this segment right here that joins the center of these two circles, if these two circles have a common internally tangent line like that, that line, it has to intersect, okay? It has to intersect this line that connects these two circles, okay? So that's a common internally tangent line. We have a common externally tangent line. See how the tangent line right here, this is it right here. Now that passes through the tangents of each circle, but it does not intersect with these two, with the line that connects the two centers. So it's externally tangent if this blue line does not intersect this here. But if this green line does intersect, if it does intersect, it's an internally tangent line. If it doesn't intersect, it's an externally tangent line. So just to keep aware of that, sorry about that. Okay. It's having a moment here. Okay, so this slide right here basically just says identify the common internally tangent line and the common externally tangent line. So just remember, this is the line that connects the two circles center, okay? If it intersects that line that connects the two circle centers, then it's a common internally tangent line. But if it doesn't intersect the line that connects the two centers, okay, then it's a common externally tangent line. So here's some examples. You have two parts to this, and so what I would suggest that you do is you pause the video for a minute and then you go through these problems. And the two things that you need to do are this. The first thing is you're going to tell whether the circles are externally or internally tangent. So that's part A. Are they internally or externally tangent? And part B is you're going to tell whether the line is a common externally tangent or internally tangent, or neither, or not a tangent. So pause the video for a minute. Okay. All right, so I'm assuming you paused the video, and let's check your answers. So for number 9, tell whether the circles are externally, internally, or not tangent. Not. See how they don't share the same center? That's a not. Tell whether the line is common, externally or internally tangent. It's externally tangent. For number 10, these are internally, see this? The circles are internally tangent. So that would be right here for this one, would be internally tangent. And part B, they are externally tangent to this line right here. So this is number 10. So number 11, okay, let me move that up. So number 11, this is not, so remember, these are concentric circles, how they all have the same center. These are not internally tangent, and they are also not externally tangent either. Because for them to be, all the points here, these would have to be all hitting the same place, okay? For number 12, this is externally tangent, and internally, the line is a common internal tangent line. Number 13, this is not externally or internally tangent, and it's an internally tangent line that is, see how it touches both, and it intersects the point where they both touch. And the last one, this is a not, and this is an externally tangent line. Okay, so here's another example. This one is just asking you to solve for x. If you notice that all radii are congruent, therefore my triangle happens to be a 45, 45, 90, which is x root 2. So this would be 4, because all radii are congruent. And this length here for x is going to equal 4 root 2. Okay, so let me circle back to my point because I was on a tangent. All right, we're going to start with tangents. So what you would do is draw a circle with center B. So we're going to draw a circle. All right, and we have circle, we have center B. Now draw any tangent to that circle. So I'm just going to draw a tangent line to that circle. Okay, and it's going to hit the point of tangency. There's my tangent line. So what I want you to do is to try to come up with a conjecture about the relationship between this tangent line and this circle. And the radius drawn from B, so let's draw a radius, B, there's B, to the point of tangency. So what are you thinking? What's coming to your head? Hopefully what you're thinking is that, yep, they're perpendicular. So it does form a right angle. So there's like all kinds of really cool things that you can do with this. And number one, we can solve some equations. Let's say this was a line segment instead of a line. There's our right triangle. So we can do some fun stuff with that. We call this the radius tangent, rad tan. That's not a real thing. But the line is tangent to a circle if and only if the line is perpendicular to the radius. So see how we have our radius here? If the line is perpendicular to our radius, okay, so let's move this over to the left so you can see. If my radius here is perpendicular to this line right here, that line becomes my tangent. So this right here is my tangent line. Okay, this is the point of tangency, and this is my radius. If the radius is perpendicular to my line here, the line is tangent. We also have something called the ice cream theorem. This is, again, not a thing. It's not a thing, okay? Not a real thing, but we call it the ice cream cone because you know that when you're eating an ice cream cone and you're holding your cone in your hand, you know that these sides have to be the same. So what's happening is you've got a circle with two lines that are tangent at a point of tangency. Those are congruent to the same point right here. See that? That value to that. So let me erase that. Because what this says is if AB and AC, so I'm going to call this A, B, and AC are tangent to a circle, D, so this is D, at points B and C, then what you know is that AB, line segment AB, remember you need the segment, is congruent to line segment AC. Okay. Now, if that's the case, and let's go back for 1 second, and let me show you one more example. Circle, if we have tangent point out here to this point out here, these are congruent. You also could have really baby little tangents here. Oh, that didn't look very tangent, but you can kind of have little baby tangents here. So like if you had a circle, right? All right, you can have a little tangent here and you can have a little tangent here where this little segment here and this little segment here, from here to here and here to here are congruent. So what that means is when you see this big shape, and don't panic, these are equal. So like you'll know 3 is congruent to this line here, so that's 3. This segment here is congruent to this segment here, so that's 6. This segment and this segment are congruent, and you know this segment and this segment are congruent. So some things that I might ask you might be find the perimeter. So you would have to add up all the sides. So this is what, 9, and this is 10. This is 6, and 3 and 5. So what do we have? 11 and 9 is 20 plus 10. I've got 30. So 30 would be my perimeter if that would be what I'm asking you. So what I have here is a couple questions. We know that CB, okay, here, let me put that back over that. So we know CB, that CB is tangent. So let's put a little right angle in here, all of these right here. So we know CB is tangent to circle O at B, check. So if OC is 2 root 17, okay, and BC is 5 root 2, then AB, so they want the whole length, okay, but we can't find the whole length at first. We're just going to find X, and then when we're all done, we're going to double it. So we're going to use Pythagorean theorem. So we're going to say X squared plus parenthesis 5 root 2 squared is equal to my hypotenuse 2 root 17 squared. And so that's going to give me X squared plus, and I'm just going to write this out, 5 root 2 times 5 root 2 is equal to 2 root 17 times 2 root 17. So this is going to be X squared plus, now remember, numbers get multiplied with numbers, so 5 is going to get multiplied by 5. And root 2 is going to be multiplied by root 2. Numbers get multiplied by numbers. Roots get multiplied by roots. So 5 times 5 is 25. Root 2 times root 2 is root 4, which is 2. So I've got 25 times 2, which is 50. And then I have 2 times 2, which is 4. And then I've got root 17 times root 17 is just 17. So 4 times 17 is what, 68? Okay, so now we just have to subtract 50, and I get x squared equals 18. I square root both sides. I get x is equal to the square root of 18, which is the square root of 9 times the square root of 2. So for x, I have 3 root 2. And so that means that line, this diameter, that's AB. So what's 3 root 2 plus 3 root 2? So that's going to be 6 root 2. So this is 6 root 2. If AB is 12, that means this is 6 and that's 6. CD is 4. What's BC? So you have to remember that this line segment you don't have, but you do, right? Because you know this line segment, that's a radius. And wouldn't you agree that all radii are congruent? So if that's 6, so is that. And so that means this length here is 10. Okay, so this is a 6, 8, 10 triangle. And if you forgot that that's 8, that's a special right triangle, right? You can still go 6 squared plus x squared is equal to 10 squared and solve that out. And then you're going to get 8 also. So BC is 8. The last one, the last problem is, oops, we really don't need this. I don't know why all of this is here. The last problem is COB. So COB, wait, COB. So this little line here. So I'm going to make this a little bit bigger. And okay, there we go. Okay, and we still had that right triangle. So let me put that back in. It says that COB is 60. So there's 60. You already know this is 90. So that makes this a 30, 60, 90 triangle. CB is 6 root 3. So this is 6 root 3. What's CD? So they want this length right here. So you know just this length right here. So you know that across from the 60-degree angle is A root 3. So A is going to equal 6. So A is happening across from the 30, so that's 6. And then this whole length right here is 2A, which is 12. Now, keep in mind, if this is 6 here, that's also 6 because those are radii. So they only want this length here, which is 6. All right, so what we have is two circles have radii 5. So we have a circle that has a radius of 5, all right? And then we have a circle that has a radius of 17. All right, that's 17. It says you have a common externally tangent segment length of 16. So I'm actually going to move this down a little bit because it just said I had an externally tangent line. And by drawing that, I'm going to draw it like this. Okay, and that length, I made it a little bit too big. That length, okay, is 16, is what it says. So I'm going to draw that in, and there's 16. All right, so it says, what's the distance between their centers? So they want this distance right here. All right, so what you're going to do is you're going to try to find out, well, you know, if I drew this straight across, wouldn't this be 5? That would be 5, and that's 5, right? So 17 minus 5, here's 12, right? You know that this length here is perpendicular because that's horizontal. You know this length is 16. So you can find this length between these two by just using Pythagorean theorem. X squared plus 12, excuse me, that's not right. X squared equals, X squared is my hypotenuse, equals 16 squared plus 12 squared, okay? And so working that out, there's my picture. This right here, remember this distance here is 5, which makes this 12, okay? Makes it a right triangle. This is 16, that's 12. You're trying to find the distance. And so just, you can work that out. The distance ended up being 20. Here's the work. You have 144 plus 256 is 400. Square root both sides, you get 20. A couple of things that are kind of interesting about some circles and externally or this is an internally, see that internally tangent line right here? What it does is it makes two similar triangles. And because remember, see how these are both right angles, angle, angle, see that? Angle, angle. And so that makes these two triangles proportional. So I can say AC is to BC as RC is to SC. So that's kind of neat. This is just basic terms, name two radii. So a radii would be AF. I can say radii AD. I could say AB. I could say AC. A diameter would be FC, so line segment FC. The best name for line ED would be a tangent. The point of tangency would be D. Okay. Which theorem says that ED is equal to EF? Okay. That's our ice cream cone theorem, etc. So here's FC is not a chord because FC is a secant. It's because, see this right here? That's a line. And it's because it's a secant. Okay. ED is a tangent. What can you say about the relationship between ED and DB? Well, they're perpendicular. All right. They're perpendicular. So start your homework. That's all I have for you today for day 1. We'll continue day 2 and day 3, which will conclude our chapter for circles. All right, good luck. Thanks for watching.